using bare metal USART to program it to the STM32 code. You can see from here, this is my code over here. We have instead of using the hull way, we're using the bare metal to program it to the STM32C6T6. Okay, so this, if you can see from here, is the base address. We have RCC base, GPIO base, and USART1 base over here. So from here, this is all our base address. Okay, from the over point of view, we can see this is my mind map actually in bare metal programming for the USART. So here is the start. We start here. Then first thing in everything, we have to enable the clock. So we have the RCC APP bus to enable register. We enable for the IOPA enable and USART1 enable. So we enable the clock. The second thing we do is we configure PA9 STX and configure PA10 SRX. So we set the baud rate, which if we use the USART bare metal USART, we have a USART1_BRR, which is a hex 341. This is registered for 9600 baud rate. Then we enable the USART for TX and RX. Then we say data able to send, we transmit the character, and we keep on looping and receive the character on the terminal. So this is a plan of the overview of how this mind map works for the USART bare metal programming here. So this is the IDE here. All these I already written. So we have a base address, which is I already mentioned, RCC base, GPIO base, and USART1 base as well. So this is all this hex address is present on here. So from here you can, if you go to the RM0008 menu, from there you can see what it is actually. So for first thing in every bare metal programming, you have to look at the memory map, they call. So we have here, which is the hex 4002.1000 is as our base address for reset and control, which is the RCC. So three things we need here for enable the USART. We have a RCC, then we have a USART1, the base address is hex 4001.3800. Then lastly but not least is the GPIO port A, which is hex 4001.0800. So this is all the base address that we needed in memory map in order to start the bare metal programming. So this is all the register we needed on the. So to enable the register, we have the offset from the base address. So you can see RCC, for example, APB2 enable register. We have a volatile unsigned 32-bit. Then we have RCC base, which is the base address. The offset for it, which is hex 18. So I already compiled all these in one document, so easy to see how it is enabled for the USART1 register and how enable the initialization of USART1. So you can see from here, the next thing, once done, we can go ahead and see our register. So this is the APB2 peripheral clock enable register, RCC_APB2 enables, which is the address on hex 18, which we already configure on our code. Then once we've done this, we can see this is the bit that we register. You see IOPA enable. When we go ahead our IDE, we can see here, which is the set on the, we set high on the bit 2. Go ahead and go back to there, and you can see here as well, which is, if you can see from here, I already highlighted bit 2 is IOP, which is IO port A, we enable it. Then we enable the USART1 enable, which is on the bit 14 as well. So you can see this how we configure everything. We have the register and bit definition. We set it high, which is involved. Then we have a GPIO A control register low, which is volatile unsigned 32-bit GPIO base on hex 0 basically. Then we have a high as well, which is on hex 4. So on the GPIO A control register, we can go ahead and look at our GPIO conf register, which is the next thing after once we've done the clock stuff. So we already done the clock stuff. We can look over the GPIO control register high and low. So from here you can see we already set the address offset, which we already set from here in the IDE. The next thing is we have the set of the register for high, CR high, which is hex 4. Then we also set as high as well. So from here you can see we already, once we already done the GPIO stuff, then we can go and enable the USART1 CSR, which is status register we call. We also have data register. BRR is I don't mention BRR is here. You can see status register. Next thing we can go and data register, and we also have baud rate register, which is the BRR. which is involved with the 9600 baud rate. So from there we can configure through this USART underscore BRR. So from here we can go ahead and enable all those bits which is involved. Okay. The same thing, we have a USART underscore CR1 UE, which is on for control register 1. Okay. So we go ahead and CR1, you can see all the offset enable. UE, which is on bit 13, we just USART enable, set it as high. So you can see it is high, which is 1. Everything is from here. Bit definition is we set it as high. So once we've done all the USART configuration here, we go ahead and we start the use. We can create our own function for following the data sheet, which is the reference manual. If following the reference manual, we can go ahead and make our own function as well based on the register address that is we already defined. Then we can, first thing we have here is enable clock, which is the RCC underscore APP2 enable register, and we set the IOP A enable, which is the IO port A enable, and USART1 enable. Then we clear the config first on the GPIO config. The next thing is the configure baud rate. So BRR, which is the baud rate register, we set it as hex 341. There's some calculation going on. So BRR is phase clock 2, it's about 8, which is 8 million. We divide by 9600, we get 833. 833 in decimal, we convert it into hex, which is hex 341. Then we go ahead and enable the USART and TX and RX here. So this is just created. Once we're done with the register function, we create a custom function USART1 set character. While not USART1 status register and USART status register for transmit enable, then we can go ahead and transmit the data register C. Then we receive character N on the terminal itself. So what USART1 sends string, then we go ahead and send all the string which is we want to send. So you can see USART1 underscore send string, hello from STM32 bare metal. We can directly send the string to the terminal, which is on Terraterm in the display. Character C, USART1 receive character, then we have received the character on the terminal. So this will be run in the while loop while pressing the reset button. Yeah. So I am the STM32Cube programmer. Go ahead and select the respective COM port after I plug in. Then we click on connect, chip ID. Yeah. So we connected to the STM32C6T6. Then go ahead and flash the code into the STM32C6T6. We go ahead browse. So I have here which my binary file.alpha file, and we start programming. Okay, file download completed. We go ahead and go to Terraterm. Open the respective COM port. Go ahead and choose the COM file. Okay, so currently it's denied. Let me change the push button to here. So I press the reset button. It should be displayed as STM32. If you hook this up on oscilloscope, basically on the TX and RX, if you see on STM32, which is a PA9 and PA10, if you hook up the oscilloscope on the TX and RX, you can see the signal is only transmit on the oscilloscope. So from there you can see the signal is transmitting USART because it currently just uses the TX to send the data to the terminal. Then you can see each time I'm pressing the reset button, you can see the signal is keep on jumping to the USART signal. And yeah guys, that's it for my video. This is how we can sort of I also actually kind of get starting learning the USART configuration, how to use it in bare metal programming. Yeah, that's it for this video. Thanks guys for watching. See you next time. Bye.